Okay, in this next unit, we're going to start covering a lot of geometry. And for years, I taught algebra, and then I began teaching geometry. And I always thought I preferred teaching algebra, but when I started teaching geometry, I really had a lot of fun with it and really enjoyed it because there's so many ways that you can make it interactive, related to real life. And a lot of students who struggle with algebra tend to do better in geometry. But there's just really a lot of fun activities, hands-on things, real life applications that you can use when you're teaching geometry. I always did a lot more projects, so it can really be a lot of fun to teach. You will be creating a Nearpod, and that's a project that covers all of the definitions in this lesson. There's a lot of definitions in this first lesson. And so part of your assignment for covering this first lesson is to create a Nearpod. And there's a whole folder on how to create that. But I always love grading those because I always get a lot of good work turned in. It's a good way to boost your grade. It is a project grade. But Nearpod is a tool that's great for you to use when you become a teacher. It's where you can create an interactive lesson. And so you're going to be covering these definitions and then bringing in interactive activities that you build into that digital lesson. When you become a teacher, you're going to have to figure out technologies, and that's also part of that project is going online and watching videos and learning how to use Nearpod and then getting creative with it while covering the definitions here. So if I had you in a classroom, I would probably hand out Play-Doh because as you're covering these definitions, Play-Doh is a way that you can make these definitions come to life. You can have students model a point, a line, a plane, etc. using Play-Doh, and we'll kind of talk about that as we go. On this, chart of definitions, a lot of this I filled in for you. Some of this we will draw in. But we're going to talk about illustrations and notations as well, and that's something that I want you to be very cautious about in your Nearpod lesson and on your exam and homework on this as well. So our first definition is a point. A point is an exact location in space, and we simply denote it by a dot and we name it by a capital letter. And so after point A, if we had another point, we would probably call it point B, even though we wouldn't have to. You can use any letter in the alphabet. But it's just denoting an exact location in space. And so to model that with Play-Doh, I would hand out some Play-Doh and students would tear off a tiny piece, roll it into a ball, place it on their desk, denoting that exact location on their desk by whatever point they have put that piece of Play-Doh on. A line is determined by 2 points, even though there are many points on a line because a line goes on infinitely. Those arrows on the end show us that that line goes on infinitely in both directions, but it does take 2 points on the line to determine the point, even though these are not the only 2 points on the line. When we denote it, you can see here, we have this line notation, which is, just a line with arrows on the end that we use to name that line. So it could be called line AB or line BA or line M. And I do need to move this over. This right here is an M and my arrow ran into my M. So that is something that I need to go in and edit and fix. But we could call this any of those 3 names. And if there were, and let me just for, sake of understanding, say here I even added another point. Give me a second, my pen is not working. Give me just 1 minute. Okay, so let's say I added a point here and I called it point C. Now I could also name this line. I could call it a C with that line symbol on the top, or I could call it CA. That would be the same exact line, or I could even call it line CB or BC. Because a line is determined by 2 points, it's named by any points, even though there can be more than 2 points on the line, but it's determined by 2 points. And I want you to realize, though, when those arrows go out, there are really infinite number of points on this line. It's just determined by the 2 points that you choose to name it. A plane has to have at least 3 points on it, because that's what's going to pull it out into another dimension and not just be, a flat line. So, you could have a point here, a point here, a point here, but it's determined by 3 points that are not all on the same line. So you could see that the 3 points that I put on there, if I called these points A and point B and point C, I could draw a line from A to B or A to C or B to C, but they're not all 3 on the same line. When we name a plane, we do use 3 points to name it, and there could be additional points. So like, let's say I put point D right here, you would still choose 3 points on the line to name it. So this could be ABC, ADB, ADC, BDC. There's multiple points that we could use to name it, but we can also name it by, I called here alpha. Where we could just call it, plane alpha, kind of like up here where we called this line M. So you can use 3 points that are on the plane, or you can name the plane by, say a Greek letter like I did use here where we call it plane alpha. There are a couple of different ways to name it, but you do need at least 3 points on the plane that are not all on the same line to name the plane. And notice we used 3 capital letters to name this. Now back to my Play-Doh illustration. If I had Play-Doh, I would have students roll it out into a line, but I would make a point to note that the line does go on infinitely, and there's really no way that we can model that with Play-Doh. A plane does as well, so you could take them and have their Play-Doh and have them flatten it out into a flat surface and kind of tell them, like your desk is a plane. But the thing about a plane is that in reality, by definition, it goes on infinitely in all directions. And, their flat surface of their desk is not going to go on infinitely in all directions. Maybe a chalkboard or a whiteboard up in the room, that's a plane. It's a flat surface with, at least 3 points that are not all on the same line, but it doesn't go on infinitely in all directions. And so their Play-Doh, we would flatten that out into a flat surface to model that, but we would also realize that by definition, it does go out infinitely in all directions. And so even though it is a plane, it is not going out infinitely in all directions. Collinear points are points that are on the same line. Any 2 points are collinear, but not every 3 points have to be collinear. So right here, all 3 of these points are collinear. And what's meant by this part in parentheses, if I had a point here and a point here and a point here, between any 2 points, I can always draw one line, But if there's a third point, there's, doesn't mean that any 3 points have to be collinear. Any 2 points are always collinear. That's why the definition of line is it's determined by 2 lines, because between any 2 lines, you can always create a line. So here I could create a line, here I could create a line, here I could create a line, but you can't always create a line with 3 points unless the 3 points are collinear, meaning they're all 3 on the same line. And when you do your Nearpod, you're going to be defining these points in your Nearpod and illustrating these points. And then you're going to want to pull in, some real life examples. And that's something that I'm going to leave up to you as you go through these and you create that Nearpod. A line segment, I've not given you an illustration, but it's a subset of a line. Because a line goes on infinitely in both directions, a line segment does not. It has 2 endpoints. And so here, we're going to draw this one. We're going to have 2 endpoints, and then we will draw the segment between them. And then we can, name this by letters A and B or X and Y or whatever we want to. But it's the subset of a line, basically meaning, it doesn't go on infinitely. It has a starting point and an ending point. But if I came up here to this line and I chopped off this end and I chopped off this end, the subset means it comes from the line. It consists of, all the points that are actually on this line. It just doesn't keep on going infinitely. So from here to here would be a segment. And then it contains those 2 endpoints and every point in between them. So you have to realize there are tons of infinite number of points in between these 2 endpoints, but it's determined by its endpoint. And when we name it, which is very important, this is segment AB, or you could call it segment BA, but the notation is above it is different because it does not have those arrows on the end. It just has, the segment symbol above it. Now, array is also a subset of a line, but it has one endpoint and then it goes infinitely in the other direction. And you still have to have, there's infinite number of points on here. So here is an example of array, or we could also go the other direction. So a subset of a line, meaning it is coming from a line. Basically, you're picking one point, dropping off one end, and so you're pulling it from a line. So if I go back here to this line, if I took this endpoint and I went this way on the line, that's array, still a subset of a line. Or I could go here at this endpoint to this direction this way, but it's still a subset of a line consisting of one endpoint and all endpoints on the line on one side of the endpoint. When we name this, we do still need to denote another point on here to name it. So like this could be A, B, and just for sake of it, this could be X, Y. So when you name this, you have A, B, and then the symbol for array above it. Notice that when I look at this, I know that A is the endpoint. If these letters were switched and this was B and this was A, then it would become ray BA because now B is the endpoint. The ray below here now is when we name it, it's XY with the ray symbol above it, but I know that the infinite end is going towards the Y. All right, a few more definitions on this video. So coplanar points are simply any points that are in the same plane. This plane has an infinite number of points in it, but any points that are all within this plane are coplanar. And you would name each of those, A, B, C, D, E, however you want to do it, A, B, C, D, E. Sometimes they'll be named for you, but points that are within the same plane are coplanar. Non-coplanar is if there's a point that's not within that plane. So here we would have points in here, that are coplanar, but this point out here specifically is not within that plane. So it's a point or a single point, any point that is not placed in a single plane. So there's many planes. There's planes all around us. You can, look in the room you're in, all four walls are a different plane. And then there could be infinitely number of planes drawn within the room that you're in, going all kinds of different directions. But if there is a single plane that you're looking at, and then there's a point that's not in that plane, that point is non-coplanar to the other points that are in the plane. And then I'm going to finish with one more definition. And then the next video will pick up with definition 10. So coplanar lines are lines that are within, the same plane, and they could intersect each other. They don't have to. They will. If these points, and we'll get into that into the next video. But like right here, if these lines keep going, you will see that they will intersect at some point. But that's not the point of this definition. This point of this definition is lines that are in the same plane. And so here I have two lines that are in the same plane. And so we call those coplanar lines, lines within the same plane. And remember, lines are determined by 2 points. So I don't have that on here, but just know that you could put, this is line AB and this is line CD. So if I ask you, name for me 2 lines that are coplanar, you would name that as line AB or BA and line CD using the correct symbol above it and say, okay, these 2 lines are coplanar because they're 2 lines within the same plane. And then there's many other lines also within that plane, but these are just the 2 that I have identified. One more thing I want to note before ending this video, because I kind of got off track. I kind of lost my Play-Doh illustration. So if you went back, to number 5, that's very easy for students to model with Play-Doh. They're going to roll out a line and it's going to have two endpoints, 2 points on the end that it stops. So that's really easy for them to model on Play-Doh. When you do array, you have to just kind of explain that array does have one endpoint, but it pulls out in the other direction infinitely. So really we can't model that physically, with Play-Doh, but you can talk about that and have students, pull out their Play-Doh in one direction. Coplanar points, you can flatten, make points and put those on a desk. So you can consider your desk as your plane, even though it doesn't go out infinitely in all directions visually. And you can just have multiple points with Play-Doh on that plane. To do non-coplanar, what they can do is they have points of Play-Doh on their desk and they just pick one point up, and now that one point that they have picked up, that one little dot of Play-Doh, is now non-coplanar to those other points.